Hello class, welcome to class number 4. We're going to be talking today about linear regressions. But before we go into that, let's first clarify what do we mean by regressions and what do we mean by classifications. We're going to be looking into different techniques that allow us to predict values from a given set of input data. And sometimes we're going to use regression techniques, sometimes we're going to use classification techniques. What's the difference between the two? As I was saying, in general, what these techniques are going to allow us to do is, starting from a set of variables x, we want to predict variable y. What classification does is that it takes a set of features, x as input, okay? And basically for each input value that we get, it's going to output a discrete value y. So for example, imagine that you have a set of features that characterize a bank transaction. The output, what you want to predict from those features, is whether the transaction is fraudulent or not. You might be looking into things like, for example, the amount, the place from where the bank transaction was made, the time, things or anomalies that might tell you whether that transaction was fraudulent or not. Say, for example, you always purchase things in DC or in Baltimore, and suddenly for 1 week you start making really large purchases from Hong Kong. That might be detected as something fraudulent. That type of detection is a prediction problem. Specifically, it's a classification problem that determines whether a set of transaction characteristics determine a fraudulent transaction or not. Okay. Another thing that we can predict is, for example, given things like the employment or unemployment rate, given things at the education level of the population, can we predict what's the socioeconomic level? Okay, so we are going to have a set of initial features like age or education or unemployment levels and so on, and those features will allow us to predict, to classify whether which one of the socioeconomic levels we have out there. Imagining that socioeconomic level is a letter from A to F, for example. That could also be a classification problem. When we talk about regression, the problem is still the same. We have a set of initial features that we are going to use to compute another feature, an output feature, okay, to predict another value. But the value that we are predicting is a continuous value. So the y that we are predicting is a continuous value. For example, imagine that we are talking about the height of a person. Can we determine what's the height of a person based on things like age or weight? Height is going to be a continuous value, okay? That's going to be a regression. The rating, imagine that we can rate giving any number from 1 to 5, but any number is acceptable as a rating. That would be also a regression. So the difference between classification and regression is mostly the type of output variable that the model is outputting, okay, or generating. If the output is discrete, we're going to use classification techniques. If the output is continuous, we're going to use regression techniques. In this class, we are mostly going to focus on linear regressions, okay? So bear in mind, the variable that we are predicting is a continuous variable, okay? That's a regression, and it's linear. Why is it linear? Let's look into that. Imagine that we have a set of points, x, y, okay? For each value x, we have associated a value y. So for example, for each age, we might have a height. Okay, the age would be the x value, the height would be the y value. Height is the value that we want to predict. You can, because it's just a two-dimensional problem, x and y, we can plot it. You would plot x versus y. And the goal, as I was saying, is to predict y from x using a linear function. That's the reason why it's called linear regression. So we want to regress on the x, we want to regress on, for example, the height. We want to predict the height of a person based on his or her age. And we're going to use a linear function to do that. That's a linear regression. So if we have the height, for example, versus age plotted, then we can go ahead and draw a line, and that line is going to be our predictor. So the red line here is the line that is going to approximate the relationship between x and y. And it's the one that we're going to use as a regression function to predict height from age. Examples of linear regressions. So for example, as I was saying, given the age of a person or a child's age, what's her height? Given unemployment rate, what's the president's approval rate? given your browsing history, how long will you stay on a given web page. Those are examples of linear regressions that are out there, and then there are, problems that the society is currently facing. When we think about the simplest linear regression that we could think of, okay, the simplest linear regression is the one that you see there in fx, in that function fx, okay? The function fx, what that function is doing is that it's basically predicting the value of y from a variable x. And the simplest linear regression is going to be that beta 0 plus beta 1 by x multiplied by x. So beta 0 is called the intercept, and it's basically the point in which the line, the regression line intercepts the y-axis. Okay, if x had a value of 0, y would be equal to beta 0, so that's the intercept. And beta 1 is what we call the slope, and the slope approximates the how much y increases every time we increase x by 1 unit. Okay? So larger slopes mean that, y increases really fast, versus really small slopes meaning that, y increases very slow with respect to x increases. That's the simplest regression, just because we have one predictor variable, one x variable, one y variable, and two different parameters, beta 0 and beta 1. In general, the linear regressions that we are going to be working with are far more complicated models. So the input data that we base our prediction on, it's not just going to be one variable. Okay, so say we are predicting the height of someone based on the age. Yeah, that can be a potential problem. But in general, we're going to predict the height based on a set of various variables. So we're going to predict it based on the age. We're going to predict it based on the country of birth. We're going to use a set of different features. Those variables that we use to predict y can be given different names. So you'll hear sometimes independent variables. Some people define them as explanatory variables because they explain the variable that we want to predict. Some people call them predictors because they predict the y value. Covariates, control variables in econometrics, and so on. But they all refer to the variables that we use to predict a given value. In general, the linear regressions that we are going to find are based on what we call multiple independent variables, meaning that instead of just predicting y from one x, we're going to predict y from a set of x values. So the general linear regression model is the function fx that you see here. We'll have a beta 0, which is again the intercept, but we will have multiple betas based on the multiple independent variables that we are going to use to predict y. Also, very importantly, in linear regressions, we are assuming that those independent variables we are assuming that they are predictive of the outcome, but in reality, they might or might not be predictive of the outcome. Okay? And in fact, what we will see when we build these models is that, some of the variables that we use to build a model are not that predictive. And so the beta value that they have is really small, meaning that the importance for that variable is going to be low. We'll see at the end of the class, we also see some other ways of playing around with the importance of different variables through regularization techniques. But bear in mind that not always all variables are equally important to predict. And also another issue that we might find is that in our model, some variables might be highly predictive, but that doesn't necessarily mean that the variable itself is predictive of the y, but rather it might be a confounding variable. So confounding variables are variables that they actually predict y. So when we build the model, they're going to be really important in the prediction model, but it turns out that they are indirect predictors. Okay? So they predict the variable, but not because they are real predictors, but rather because they are correlated to another variable, which is a direct predictor of y. Okay? When we talk about predictors or independent variables, they don't necessarily need to be something that, it's readily available. So it doesn't necessarily need to be age or height, which we can measure easily. But it can be more complicated variables. So sometimes we can use things like, for example, number of users in a social network or number of posts in a social network to predict what's, the importance of the message, for example. And these features are features that, we need to write some code and basically are measures that are not directly available, but rather we need to make some types of computations in order to get that value. And also we can apply any type of transformation. So sometimes instead of using just a plain variable, we'll use its logged value. We might use basis expansions of the variables. We might use indicators, whether something happens or not. So that's this variable, take values between -1 and 1, yes or no. So binary values that are indicators of events, or even interactions between variables. Okay, so what's the product of x1 and x2 that might be predictive of y. So when you decide to build your predictive models for, say, milestone 1, when you think about, what you want to predict, sometimes the variables that you will think about are not necessarily very simple variables, but they might be more convoluted, more elaborated variables that you want to work with. Now, so if linear regressions are basically trying to find a line that will approximate, the values x and y that we are observing, which line is the correct line? So when we write the command linear regression in R, what that command is actually doing is looking for the best fit. It's looking for the line that best represents the actual observations. How do we do that? And not only in R, okay? In any type of package, machine learning package that you use, it's exactly the same math. So the idea of finding the best fit is based on minimizing the loss on the dataset. Okay, so the way this is done is that empirically we take a dataset, we divide it into a training and a testing dataset, and what we do is that we take the training dataset to find the best fit. And then once we found that best fit, we basically use it as a predictor in the testing set. And we'll see examples of this. Don't worry. So the way we define a loss function, okay, is basically computing the difference between the real y values and the values that our fitted function outputs. Remember that fx is the fitted function that's going to represent the linear regression. So the loss function is going to compute the difference between the actual values and the predicted values. And what we call empirical risk, the empirical risk is the average loss over the whole data set. So if you compute the difference between y and f of x for every single point, that's the empirical risk. So in order to minimize the loss, okay, we need to first define what loss is. As I was saying, the simplest loss that we can define, it's the difference between y and fx. The simplest loss that we can define is the squared error from the y value. So if you look at the last line in this slide, the simplest loss function is going to be the difference between y and f of x across all different values of x and y. And it's the squared difference between the two. You can define other loss functions, okay, and then you can basically find for a fit with other types of loss functions. In this class, we're going to be looking into the squared error. So what we are actually saying is that if our actual data are the red dots, what we are computing, the error that we are computing is basically the distance between the actual dots and the line. The black line represents the linear regression. So the distance between the red dots and the black line are the errors or the residuals, okay? And the sum of those errors is what we want to minimize, is the loss that we want to minimize in order to find the best fit. In order to fit, let's take the simplest case, okay? We begin with the simplest linear regression, which is just the regression that depends on one unique variable. We have the x variable, okay, and then we have theta 0 and theta 1, the intercept and the slope. What we want to do is minimize the loss or minimize the empirical risk. So what we do is that we sum the differences between the actual y values and the values from the fx function. So in the second function there, r of theta, what you see there is the empirical risk or the difference between the actual and the predicted values, a squared difference. And what we want to do is actually minimize that risk. And that minimization is going to give us the values for the intercept and the slope that are going to represent the best fit function. Again, when we are looking for the best fit, basically what we are looking is for the best theta 0 and theta 1 parameters. We need to look for the intercept and the slope. That's what looking for the best fit means. Okay. How do we do that? So just, from calculus, the way we look to a minimum is by looking at when the derivative of that function equals 0. And when the derivative of that function equals 0, that's the minimum, okay? And the values that give us that minimum are going to be the values for the intercept and for the slope. Once we have found the values for the intercept and the slope, okay, that's going to be our predictive function. We've computed it with the training data. What we need to do is basically, with the testing data, trying to understand how well we can predict the testing data using that function. Okay, so we just need to find the point on the line that corresponds to the new input. So if we have found that the fx function has as intercepts theta 0 and theta 1, we are going to use those values to output the predicted value. And again, we'll see examples in R about this. So imagine that we start with a set of points, which are the white, black dots. We compute the best linear regression. The best fit is that dashed red line, which is y equals 1 plus 0.5 times x. We have computed this linear regression with training data, and now we have a new point, which is x equals 5, and we want to see what's the y value, and the y value would be 3.5. That's the way we use the points to train and the new points to test. So imagine that we were computing, what's the height based on your age. We use different training data, and now we say, okay, we have a child who's 5 years old. What's going to be the height? 3.5. It doesn't make any sense numerically, but you understand where I'm going.
Another way of understanding how linear regression models are fitted is by basically looking at the distribution of the residuals, or the difference between the actual values and the predicted values by the model. Because for linear regressions, it is required that the distribution of those errors follows a Gaussian or a normal distribution. Okay? Visually, the way we express this is that basically we can look at the fitted line, which is going to give us the predicted values for any given input x. And the assumption in linear regression models is that the distribution that characterizes the differences between the y's, the output values, and the predicted values by the linear model, by the line, that relationship is going to follow a Gaussian distribution. And what you see here, it's basically the representation of the different conditional Gaussians for the different mean values in the linear model. And so what does this mean? So this is just important because some of the packages that you will run, the way they might approximate the best linear fit, instead of using the minimization of the total error, could be the maximization of the likelihood of this conditional distribution. What do I mean by this? So far what we've seen is that in order to understand what are the best parameters for a linear fit, right, the best beta or theta parameters, generally what the models internally do, the libraries that you use in R, in Python, or in any other languages, what those packages do is that they look, their main objective is to basically minimize the difference between the value predicted by the fitted model and the actual value, right? So the approach there is an optimization problem, and we need to minimize the total error. However, following a probabilistic interpretation of what linear models are, which is mainly focused around the errors following a normal distribution, there's another way of optimizing to find the best linear fit. And that other way of optimizing is by looking at the maximization of the likelihood of PYX. What does the likelihood of PYX mean? So basically, what that does is maximizing how the distribution of the errors is as close as possible to a Gaussian distribution, right? And so if you look at the formula there, that likelihood there, what the objective in that likelihood is not minimizing the error, as we've seen, but rather what we are doing there is maximizing the likelihood that the values approximated by the fitted linear model, the xiw, and the actual values, the yi, are as close as possible, the difference between the two are as close as possible to a Gaussian distribution. Remember from last class, the formula for a Gaussian distribution expressed as an exponential, like the one that you see here. So what we are saying is maximize as much as possible that the relationship between predicted and actual values, that is the error or the residuals, follow a normal distribution. Try to fit those differences between predicted and actual values as a normal distribution. And some packages out there, what they do is that they use a probabilistic interpretation, and rather than minimizing on the error, they will maximize on this likelihood. They will maximize on the distribution of the errors, following as much as possible a Gaussian distribution. Again, this is not something that I will ask you to run, I will ask you to prove, but I think that it's important for you to understand that where you are running these packages, it could be the case that different types of optimizations are taking place. And oftentimes you will get slightly different results if you run different packages, because maybe they are running internally different approaches to optimizing or to finding the best linear regressions.